Hi. In this video, we're going to talk about mixed flow reactors of different sizes in series. Now, in another video, I have already taken up the question that how to find the conversion for a given configuration of mixed flow reactors of different size in series. In this video, I'm going to consider the question of determining the best system for a given conversion. Okay, so suppose we want to find the minimum size of two mixed flow reactors. Okay, let us start with the simplest case of two mixed flow reactors in series, and our target is to achieve conversion x. Okay, and another thing to note that we already know about the kinetics of the process. With that knowledge, we are going to proceed forward. Okay, now here once again, like I have said previously, the first thing that we need to keep in mind is the design equation. So I'm just going to write the design equations for the mixed flow reactors. V by Fa naught, where V is the volume of the reactor, Fa naught is the initial molar feed rate, equals to tau by Ca naught, where tau is the space time, Ca naught is the initial concentration, equals to Xa by minus Ra. Okay. Xa is the uh, conversion of component A, and minus Ra is the rate equation. You can also write this as tau equals to Ca0 Xa final minus Xa initial by minus Ra. Okay. Now proceeding to the main concern. So, since I have said that we have two reactors at hand, so we'll just write the expression for its space time first. So, tau 1 is simply C0 x1 by minus R1. Okay. For tau 2, you can write C0 x2 minus x1 by minus R2. These are fairly simple, obtained from uh, the design equations of the problem. Okay. Now let us draw two different configurations which actually take us to the same final conversion of x2. Okay. So one configuration can be like you have a small mixed flow reactor first. So here you have initial conversion of 0, C0 and F0 at the inlet. From there you have the outlet which goes to a larger reactor. So here intermediate conversion is x1, and here you have okay, one thing, this is tau 1 v1 over here, and this is tau 2 v2 over here, and the final conversion is x2. This is one configuration. Okay, and the other configuration is the larger reactor first. Spare my drawing skills please, because I'm not really good at drawing. It's just a diagram anyway. So is equals to 0, initially C0 F0. So this is tau 1 V1, and then the intermediate conversion is X1, and then we have a smaller reactor of tau 2 V2 with final conversion X2. Okay. Now we have assumed that in both the cases this final conversion X2 is the same. In that case, we choose which system is better for us. Okay. So for that, if you remember the graphical procedure for determining the size of the mixed flow reactor, then what we do is we simply draw a plot where on y-axis we have conversion x, and on on x-axis we have conversion x, and on y-axis we have minus 1 by r. That is the reciprocal of the rate expression. Okay. So with that, let's say we get a curve like this. Okay. At this point lies x2. At this point lies x1. So now you have to draw a rectangle. So the area of the small rectangle, this is equals to tau 1 by c0. Okay. This procedure I have discussed before. You can go through some of the other lectures where I discussed about determining the size of steady state mixed flow reactors. So if you find the area of this rectangle, then you will get tau 1 by C0 value, which is also equal to F1, sorry, V1 by F0. This is from the design equation. Similarly, for this second reactor, if you just draw another rectangle, so that rectangle will start from here to here. So if you find the area of this entire rectangle, then you will get tau by C naught quantity, which is again equals to P2 by C naught quantity. This is fairly simple. Okay. Same thing if you do for the next case, for the second case. So again, you draw this is conversion x on the x axis, and on the y axis we have minus 1 by r, and we have the same rate curve. Then from the first reactor we have conversion x1, and from the second we have conversion x2. Okay. So for the first reactor, uh, this would be the rectangle, and this area within the rectangle will give us tau 1 by c naught was v1 by, and the second one area will give us tau 2 by c naught equals to v2 by f. Okay. Now how do we know which reactor is better? See, as this intermediate conversion changes, the reactor volume is also going to change from this procedure of determining the volume of the two reactor vessels. Okay. Therefore, if we want the total reactor volume to be as small as possible, then we have to maximize the area of this rectangle, this shaded region has to be maximized, because if this shaded region is larger, then automatically the other two regions will be getting smaller. The other way to put this is, we have to find this point, the point that I am boldening up, this point on the curve, such that the area of the rectangle over here, let me call this rectangle A, B, C, D. So the area of the rectangle must be maximized. Such way we have to choose point C. Essentially, we will be choosing the intermediate conversion x1 in such a manner to determine the minimum size requirement. Okay, so for that we need to maximize the area of this rectangle ABCD. So then this becomes a simple maximization problem. Okay, we call this concept the maximization of rectangle. Okay, now how do we maximize the rectangle? See, we have to find this point C, right? So this C is a function of both x and y coordinates, right? So let us just outline the procedure of maximizing a rectangle in general. Let's say you have a plot On x axis you have x, and on y axis obviously you have the quantity y, and this is the arbitrary curve. Okay, so let's say you want to find the point C on this curve, such that the area of this rectangle that forms over here is maximum. Okay, then first thing you write is the area is simply x into y, length into breadth, simple concept. Now you take differential, so you can write it as dA equals to y dx plus x dy, and the area becomes maximum when dA equals to 0. That is the basic concept of maxima minimum for finding the stationary point, right? So this should be equivalent to 0. We are essentially finding the stationary point. So to find that, you will get minus dy by dx equals to y by x if you solve it. And this condition means that the area is maximized when point C is at that point where the slope of the curve, that is, if you draw a tangent. Okay, I drew it a bit far from the curve. Let me draw it. So if you draw a tangent, then the slope of the curve at point C and this diagonal of the rectangle should be equal. Okay, these two quantities, this line over here and this slope of the curve at point C, they should be equal. Okay, so depending on the shape of the curve, there will be either there will be no best point, but if you have the nth order kinetics, okay, where n is greater than 0, then there will be at least one point. There will always be this one best point to maximize the area of the rectangle. Okay, so the optimum size ratio of the two reactors that we were discussing earlier will be achieved where the slope of the rate curve equals the diagonal of that rectangle ABCD. Let me relate it to this figure. So what I just said is that the optimum size ratio or the minimum size requirement of the two reactors will be achieved when the slope of the rate curve at point C will be equal to the diagonal dB. So if this is the slope and this is the diagonal dB, if these two becomes equal, then you have the maximum rectangle. Okay, and this value of C that we'll obtain will help us achieve the best intermediate conversion to, you know, optimally size the reactors. Now in general understanding about this case, what are the observation? So the main observation is that when we have first order kinetics, okay, if you have first order kinetics, then you should use the equal size reactors. So the process that I outlined is the graphical procedure, but let's say we have some general takeaways from this entire procedure, so I'm just writing that down. So first order kinetics, you require equal size reactors. Okay, for orders when n is greater than 1, the smaller reactor comes first, smaller followed by larger reactor. Okay, and for n less than 1, we have larger come first and then the smaller reactor. Okay, but in a very practical point of view, it was seen in the industries that mostly the equal size system is always preferred. Okay, because of economic considerations. That is why when we are practicing it in theory, we generally tend to follow these norms, but when we are industrially, applying the process, the trend is that we follow the convention of equal sized reactors. That is it for the second design question of unequal size mixed flow reactors. That is how to determine the minimum size requirement for a given conversion. That is it. Thank you.